See, we have two questions here. They are very famous questions of the book HC Verma. They deal in very basic units and dimensions, but the questions are very, very beautiful. The first question is a dimensionless quantity. It's asking about a dimensionless quantity. See, a quantity, physical quantity Q, can be dimensionless if all the dimensions of mass, the dimensions of length, the dimensions of time, the dimensions of current, etc. If you want to add another dimensions, you can add, but primarily you have to learn about these three. So we are restricting our discussion to these three. So the dimension of each of these three should be 0. Now mostly this can happen as this physical quantity Q can be product of many physical quantities, or it will be in the form of A into B into C, something like that, divided by D into E into F. These are all are some physical quantities. Now regarding dimensionless quantities, I will give you two examples which will make it easier for you to choose the correct option for this question. See, there is a quantity which is relative density. Relative density is density of one fluid or density of one substance divided by density of other substance. Usually there is water in the denominator. Now the unit of the quantity in numerator will be kilogram per meter cube, the usual units of density, and the unit of the second quantity in the denominator will also be kilogram per meter cube. Now both will cancel out and you will find it with no unit. So relative density or a specific density is said to be 0.9 or 0.8, 0.2. There are no units with it. But at the same time we have some quantities, like one is concentration. Concentration of a solution, if it is quoted weight by weight, what this means is there is weight of solute in the numerator and there is weight of solution in the denominator. Now you see in the numerator also you have weight, which will be quoted usually in mass, kg or gram, and in denominator also there is mass, kg or gram, whatever you want to write. So in the numerator also you have kg and in the denominator also you have kg. Both will cancel out, but when you see the concentrations being quoted, you will see something kg of solute per kg of solution. So this has a unit, even though if you use the dimension of mass here and dimension of mass here, they will cancel out. It will be a dimensionless quantity, but it has been quoted with this unit, kg per kg of solution. There is another physical quantity, specific humidity. You might not read it in your level, but it is usually in engineering levels. A specific humidity, W, is quoted as mass of water vapor in the air. Mass of water vapor in air divided by mass of 1 kg of dry air. What happens is, in a room, suppose you isolate this much amount of air. Now in this air you know very well that there is dry air plus water vapor. Water vapor, which is usually moisture. If the moisture is high you will feel very humid, and if the moisture is less you will feel very dry, as in winters. Now the specific humidity is mass of this divided by mass of dry air. So in the numerator also you will find something kg, and in the denominator also you will find something kg. But this is kg of dry air. dA means dry air. The unit of a specific humidity becomes something kilogram per kg dA. per kilogram of dry air. So this becomes the standard unit. Everybody uses this unit, but the quantity is dimensionless. In the numerator also you have mass, and in the denominator also you have mass. Both will cancel out. Dimension will become 0. So this quantity is dimensionless, but this has a unit. So you got two examples where one dimensionless quantity did not have any unit, and one dimensionless quantity which has a unit. So being dimensionless does not make sure that you will not have a unit. A dimensionless quantity may also have a unit. So the correct option is C. The other question is about a unitless quantity, a quantity which has no unit at all. This can always happen only when this can only happen if it has no dimension also, because unit implies dimension. What happens is, it is saying that there is a physical quantity, it can be measured, but there are no units attached to it. There are no units attached to it. Okay, for example, number of people, you will quote it as 4 or 5, you will say 10 people or 15 people, but there are no units attached to this. These are just numbers. So these are just numbers, and this implies that it will not have any dimension also, because dimension is always attached with units. Okay, so if there is no unit, it will have 0 dimension. There will not be any dimension attached to it. So you will have to read the options very carefully in this question. This question is more beautiful because of its options. The first option is never has a non-zero dimension. Never has a non-zero dimension means it always has a 0 dimension. This statement means never has a non-zero dimension. कभी भी non-zero dimension नहीं होगा, मतलब कुछ ना कुछ डायमेंशन होना चाहिए, जबकि ये इसका ठीक उल्टा इन्होंने बोला है, never has a non-zero dimension. It means it always has, this statement also means always has 0 dimension. अगर आपके पास कभी भी नॉन ज़ीरो डायमेंशन नहीं है, मतलब हमेशा आपके पास कैसा डायमेंशन है, 0 डायमेंशन. सो पहला ऑप्शन ही इसमें करेक्ट होगा.